This video will present some of the research conducted in the Graphical User Interfaces for Blind Persons project, funded by the Commission of the European Union. For users who are blind, the development of inexpensive machines with command-line interfaces allowed them to use computers very successfully. A one-line command maps easily to synthetic speech or a braille display for the output medium, and blind users are proficient with standard keyboards for input. Blind users also require some screen reading software which produces the screen text in either synthetic speech or braille, and also provides functionality to explore and review the screen contents without actually executing commands. The increased popularity of GUIs may have made computing easier for many sighted users, but for their blind colleagues this development has been a drastic step backwards. Imagine trying to use a GUI if you could not see its many visual aspects, such as icons, windows, or the location of cursors on the screen. Blind users see GUIs as adding an extra layer of complexity to the interface, which will be of no advantage to them. Many blind users and sighted experts believe that the visual metaphors used in GUIs, such as icons and windows, will be difficult for them to understand. Sighted users develop conceptual models of the interface on the basis of visual information it provides and their knowledge of objects in the real world. Blind people effectively manipulate objects in the real world, so why shouldn't they use this ability in the computer interface? Their conceptual models could develop on the basis of auditory and tactile information. One of the great advantages of GUIs for sighted users is the ability to directly manipulate interface objects. How can we create interfaces for blind users in which direct manipulation can be carried out on the basis of auditory and tactile information? However, the characteristics of visual information are very different from those of auditory or tactile information. Visual information gives us a very rich, spatially organized representation of a scene. It allows us easy access to both an overview or specific details. Like visual information, tactile information is spatial in representation, giving us a detailed knowledge of the world at our fingertips, but is unable to provide the same overview of a scene obtained from a visual glance. Auditory information, on the other hand, has a more temporal organization, and we can only attend to a limited number of sounds simultaneously. These different characteristics of sensory modalities need to be considered in developing intuitive and efficient non-visual interfaces for blind users. The overall aim of the GUI project is to develop interfaces for blind users which will give them the same kinds of advantages which sighted users already have with GUIs. In particular, to create a sense of engagement which comes from the direct manipulation of interface objects. To do this, users will need certain kinds of information about the visual interface, for example, its spatial layout. Thus, in the GUI interface, this kind of information is preserved rather than presenting the interface in an alternative form, such as a tree structure. We are investigating how visual information can be translated most effectively into a number of different auditory and tactile forms in order to cope with the richness of the original visual display. We are exploring the use of synthetic and digitized speech, non-speech sounds, both natural and abstract musical sounds, and braille and a touchpad to produce a multimodal display. In order to give blind users access to the information in a GUI, the bitmap visual presentation must be converted into a form with which blind users can interact. To do this, the GUI project has developed a representation mechanism to describe interaction objects used in applications and the dynamic changes in these objects. This so-called off-screen model is used to generate a text-based presentation suitable for non-visual input and output. Graphical objects are represented with ASCII characters such as brackets and text labels. For example, a checkbox is indicated with brackets and an X, and the system menu of an application with an asterisk. A visual form of the presentation can also be produced to enable successful collaboration between blind and sighted users, for example at work. The project has also developed software to allow blind users to interact with the system via the off-screen model. This is equivalent to the screen reading software in command line systems, but must now cope with both input and output. Let us now look at how the GUI system attempts to create direct manipulation using two forms of tactile information. The touchpad gives the blind user a spatial overview of the screen similar to the visual glance of a sighted user. Touching the pad lightly produces speech informing the user of the interaction object at that location on the screen.
Group with face.
Pressing more firmly emulates moving the mouse to that object,
Group with face.
which can then be activated with a key just below the touchpad. Direct manipulation at a much finer level of detail can be achieved using the Braille display. A Braille module comprises 8 independent pins in a 2x4 matrix, which represents an ASCII character by moving the pins up and down. There is also a small routing button above each Braille module, and pressing it moves the cursor to this location, a process known as cursor routing. The GUI Braille display includes 2 rows of 80 Braille modules and a vertical display based on Braille modules, which is used to give information about cursor positions and the quantity of information on each line of the screen. The 2 rows of Braille can display 2 lines of the screen, and as the cursor is moved in the interface by input from the keyboard, touchpad or routing buttons, the lines of Braille track this cursor. A fundamental difference between visual exploration of the display and exploration using Braille is that whereas the sighted user may move the mouse about the screen freely, the blind user can only move the mouse cursor in discrete steps by clicking on different routing buttons. For example, to move the inactive window Wind Train, the sighted user moves the mouse into the window and clicks the mouse button once, making the window active. The blind user, on the other hand, must click twice on the routing button, once to move the mouse cursor into the window title, and again to make the window active. To pick up the window and move it, the sighted user presses the mouse button and holds it down while moving the mouse to the desired location. She then releases the button, which drops the window. The blind user executes the pickup by double-clicking on any other routing button. To move the window, she then scrolls down the display and double-clicks on the destination routing button to drop it. These forms of interaction have been assessed along with other components of the GUI interface in a systematic evaluation. This evaluation uses standard sets of tasks in 2 common application areas. 16 blind users have each undertaken 4 hours of training in GUI concepts and the GUI interface and 4 hours of evaluation. Extensive objective measures such as time taken to complete tasks and error rates, and subjective measures such as ratings of the components are currently being analyzed. For example, users were asked to rate the different input methods. They rated input from the keyboard most favorably, probably because they were already familiar with this method and it is very reliable. The touchpad was not rated as highly, perhaps because users often found it difficult to locate individual interaction objects on the small touchpad. Further design work needs to be undertaken to attempt to improve its usability. The routing buttons were very highly rated, and many positive comments were made about this method of interaction. For example, one user said that he liked using the routing buttons in dialog boxes as it gave him a proper hands-on feeling. A number of other users commented on how efficient and easy the routing buttons were to use. These comments are similar to those from sighted users about direct manipulation techniques and indicate that blind users are really achieving a similar sense of engagement with the system. Other work in the GUI project is complementing this research on direct manipulation. We are investigating the potential of a number of novel input devices and the use of three-dimensional sound and speech output to create a virtual sound display. In conclusion, the GUI project has shown that there is reason to be optimistic about the potential of blind people effectively using GUIs. With appropriate training, particularly in the metaphors used in GUIs, and suitable interaction techniques based on auditory and tactile information, blind users will be able to have at least some of the advantages of GUIs currently enjoyed by sighted users.